Okay, Pascal's law states that the pressure in a fluid is transmitted undiminished to all points within a volume of fluid. So Pascal demonstrated this law by considering the pressure on a small prism of fluid. Now we could demonstrate this by saying, let's take a cubic volume of fluid like this, and we'll give it a third dimension, and let's say it's underneath a larger volume of fluid, and we're just considering this little cube at this point here. There we go. So that's our cube of fluid. Now we could say, look, the fluid has a pressure coming from this side, and a pressure coming from this side, and then there's a pressure on this face, and then there's one on this face. So this would be Py, negative Py, and this would be Py, and this would be negative pressure in the x direction, and this would be pressure in the x direction. Now, of course, pressure is a scalar, and Pascal's law is basically telling us the pressure is at any point in the fluid is acting equally in all directions. You know, the scalar doesn't give us any direction to the pressure. So to prove that, we would then say, well, look, if negative px and px are the same, how do we do that? If with a scalar, what we can do is convert it into a force and just show that the force in the x direction and the force in the negative x direction cancel each other out. So let's do that. So I'm going to do this. I'm going to say, look, the force in the x direction is going to be F in the x direction will be equal to px multiplied by this area. You know, force is the pressure times the area, so px times whatever that blue area is. And likewise on this side, it's going to be negative px multiplied by that area, and then for py coming up, it'll be py multiplied by that area, and then finally for negative py coming down on the cube, it's going to be py multiplied by that area. Now, if this cube was really, really small, then we would know that the pressure isn't actually changing with height. Okay, so let's say the cube is tiny, so small that the change in pressure from this point to this point is just negligible. Then we'd be able to say quite easily that the force in the x direction equals the force opposing it, the collinear force, the negative force in the x direction. So Fx equals negative Fx, and then the same in the y. Fy equals negative Fy. And we've proved that the pressure acts equally in all directions at any given point in the fluid, Pascal's law. But mathematical proofs like this are no good because that only works for a cube shape. We want it to work for any shape, and then it's more generic and general and can be applied. So what Pascal did, and he did this, Pascal was a genius, I am not. Legend has it he did this before his 16th birthday. So let's just very simply discuss what he did. Now, for those of you who ain't so good at the old maths, that's fine. This isn't really that mathsy. What's important here is understanding where these theories, where they come from and what they actually mean and how they therefore dictate a lot of the physics or the engineering that you will then do, which is more advanced. Understanding these theories from a pure mathematical derivation from the fundamentals is not what this it's not what I'm trying to do here or on this channel. I'm trying to make sure that we can have some confidence that we know, even if we couldn't do it, if we were asked by someone to just derive it there and then, we do know and we do trust in our confidence of that knowledge that we know where this theory comes from. And that's going to give us two things. It gives us a good background knowledge of theories, which for engineers is good for practicing, because we need to come up with the solutions. So a good knowledge of the theory is essential. But B, and most importantly, it gives us the confidence that we just don't have to take it as a given that this is the case, Pascal's law is the case. We know, we understand the physics behind it. And confidence helps us do better, but it helps us enjoy what we're doing rather than it being sort of panic-inducing every time we have to do our studies. We start to enjoy our studies, and if we enjoy our studies, then we inevitably will do better at them. So Pascal did this with a triangle, triangular prism, because he wanted to prove that the pressure on all sides of this at any point in the fluid are going to be equal. And the way to do that is to do it for any angle theta in a prism. Obviously, if theta becomes 90 and this becomes a square, like we just did, it's very easy. But what about for anything between 90 and 0? Does it still balance out this pressure here, and this one here, and then this one here? And the answer is yes, and this is how we did it. That would be px, and this would be py. So I'm calling this ps because to separate it from x and y. It's not so clear to us how px equals ps, and which equals py, and all these are the same, because they're at different angles. They're not collinear. So again, we need to turn them into forces, to vectors, and then do some what we call vector calculus to add and subtract these vectors. Excuse me. Now, before we do that, we're just going to define this triangle a bit better. So if I start off with just the x direction, so I'll make a 2D triangle, I'm going to say, look, this surface here is called delta x, delta s, delta y, and then this one here, giving it that thickness in there, is delta z. So look, we need a coordinate system. That's going to be the x coordinate, and this is going to be the y coordinate. Now it's in 3 dimensions, so I'm going to give it a z coordinate into and out of the page. And of course this is called s. But what is this delta business for? What's this symbol about? Now again, that might, for those of you maybe who haven't done a lot of maths, might induce a little bit of panic. But in this case, so this is a small letter Greek delta. In this case, all it means is that whatever's on the right-hand side of that symbol is what we would term infinitesimally small. Now, the concept of that is that if I'm going to say delta x, so an x, if it didn't have delta, would just be a value in meters, right? The length of the bottom of this prism. If it's delta x, it means the value in meters is fundamentally it's 0. So it's what we call infinitesimally small. Now again, that rather than it being mathematically confusing, that might be sort of conceptually confusing to us. But in order to make this proof work, we need to reduce the size of that prism to effectively nothing. Now we can still add and subtract all these vectors that we're going to make, but we're assuming that these lengths are so small that actually the forces on them are effectively 0. And while it might seem a little bit confusing, hopefully it becomes clear when we complete this proof of the theory. So delta x simply means the value in meters of x is effectively 0. All right. So I've got this large prism here, which I've drawn, and The angle is that. Now I want to focus on the balancing the value of px, which is in the horizontal, with whatever with ps here, which is coming in this direction. So how do I do that with Pascal's law? We basically need to turn these pressures into forces, because then we can add and subtract those vectors of forces. So in order to turn any force has a component that can be divided into two components. Let me just get another slide here. I'm just going to delete there. Oh dear. Let's get rid of that. And that one. Okay. So if I had, for example, if I was pulling a trolley along, like a cart, and I was pulling it with a rope. This is my rope, and I'm pulling it this way. So I'm applying a force actually with this rope, which can be depicted as a vector of whatever that force is. And we can call that force F, the resultant force. Now, because I'm taller than this trolley or this cart, my rope is off the horizontal by an angle theta. Now that means if I do it in a slightly, if I just get a different color, that means that this force which I'm applying to the rope, Fr, can be divided into two subcomponents. This one, which is how much of that force goes into pulling it in the horizontal, and this one, which is how much of Fr is pulling it in the vertical, Fy. So how would I work out those forces? Well, I'd use my trigonometry. So I'd do Fr is equal to the square root of Fy squared plus Fx squared. And that is just C is equal to the square root of b squared plus a squared, right? So that's just Pythagoras' theorem, because these vectors make a triangle. Fr being the hypotenuse, Fy being the opposite side, and Fx being the adjacent side. So then, in order to take our pressure from our prism, like this, so that PS1, and turn that into a component which we can deal with of force, we would, which is going to be equal and opposite to whatever this force is, which is going to be pressure in the x direction multiplied by the area, and that area is going to be delta y, which is this length, and delta z, which is that third dimension. So let's just write that down. So Fx equals Px times delta y delta z. I can't do that. I need to turn PS. I can't do this minus whatever PS is. I need the I need PS in this direction. So what component of PS, the pressure on this surface, is pushing that prism in the x direction along that x coordinate, which is collinear to this pressure and therefore this force? We could call that negative PS in the x direction. And look, it is the opposite side of a triangle. It's the opposite side of this triangle here with this internal angle. And that internal angle is the same as the main one. Okay, that's just geometry. So we can say, look, all right, so PSX must be equal to the pressure in the s direction, which is the hypotenuse, multiplied by the sine of the internal angle. Why is that? Because sine theta equals the opposite over the hypotenuse. In this case, we have the hypotenuse, that's PS. We don't know what the opposite is, which is PSX. So we would multiply PS by the sine, like this, to get whatever PSX is. So now I've got the pressure component of PS in the x direction. I'm going to call it negative because I have to give it the opposite sign because it's acting in the other direction to my PX multiplied by A, my force in the x direction. It must have a negative sign. And, you know, that's just my decision, which one's positive and negative, but you must decide which, you must make sure that if it's acting in a different direction to whatever your positive direction is, you give it the opposite sign, the negative. So that's the pressure in the x direction. So the force is going to be that pressure, so negative Fx equals negative PSX multiplied by the area, PSX multiplied by sine theta, so that's our that's our pressure on the x direction. Then that's multiplied by the area, which is going to be, going back to this one, it's going to be this area here, so delta z multiplied by delta x. Delta z, delta x. Alright, so we've got Fx and negative Fx. Now we need to, Pascal shows that those two cancel each other out, so Fx should equal negative Fx, but how? This one's got lots more to it than this one. Let's I should have prepared these extra slides earlier. Let's do that. And this one. Right, so let's just write that out again. So I've resolved this to Fx equals P in the x direction multiplied by delta x delta z, and that must equal negative Fx. I'm just going to do that. Hang on, I'm just going to say equivalent to, so I don't make it into one big equation. It's equivalent to negative Fx equals P Sx times sine theta multiplied by delta z delta s, right? I need to turn this trigonometric ratio sine theta into the actual values of the triangle, okay? So we can just consider, remember, sine theta equals the opposite, as I mentioned, over the hypotenuse. And in this case, the opposite of this angle here is going to be delta y, this one here, and the hypotenuse, of course, is delta x. Delta s, sorry. So we can then say delta y, delta s. So now I'll just take that here and substitute it into here, like that. So then I can actually manipulate it. So let's do that. So I'm going to remove this and put delta y over delta s. Now we're getting somewhere because the next thing I can do is cancel this out. That one and that one cancel out. So I'm left only with delta y times delta z. So removing all that. And let's rewrite it. So we've got px multiplied by delta x delta z equals negative p sx multiplied by delta y delta z. I've got that wrong. That's a delta y, not a delta x. Sorry. I think, did I get it wrong in this bit here? I did. Delta y, delta z, and this one should be delta y, delta z. I did delta x, z, so it's correct in the original. I've just written it incorrectly there. So obviously, all of these are the same as all of that, so they will cancel each other out as a force. So Fx equals negative Fx. And that's how Pascal has balanced the forces and shown that, you know, even if you've got a pressure in this direction and a pressure in that direction, they actually are equal. Now he does it as well on the y plane. So I'll go through that quickly now. I'll try and be quick. But it's basically exactly the same. Just instead of the sine, we need the cosine because we're going to be looking at a different side of our PS. So we've got PS, and in this case we want to do the adjacent angle, which is going to be going like that. We did that one before. So the adjacent angle is, the adjacent side, this one is going to be PS cos theta, PS in the y direction, times cos theta will give us that one. So obviously coming up you've got Py, we're going to call that the positive one, we'll call this the negative one. So Py as a force is going to be Py multiplied by delta x, which is this bottom one here, that one, times delta z, which is the third dimension, so it's going to be delta x times delta z to give us that surface. Okay, and then this one coming down will be delta, so that will be multiplied by delta s times delta z, giving it that surface there. So negative Fy equals negative Psy cos theta delta s delta z. Cos theta, we need to change that like we did with sine theta into the actual values, and in this case it's going to be cos theta is equal to the adjacent side over the hypotenuse, which is equal to delta x over delta s. So cos theta becomes delta x over delta z, delta x, delta z. And then of course this one and this one now will cancel out. Sorry, delta s, not the x. Delta s. It's not the z's that cancel out, silly. S. So it's that one, delta s. So this one and this one will cancel out, leaving just delta x, delta z, which is the same as here. So you've got positive Py is equal to negative P sy delta x delta z. They should balance out. Now, the third thing you might consider coming down is the volume of the fluid, the weight. Weight force. Weight is a force, it's a mass times acceleration. So the weight of this prism is going to be the negative F weight force equals density times gravity times the volume of the prism. Now, because the volume, which is going to be 1/2 times delta x delta y delta z, as in 1/2 of a square or a cube of delta y z delta x, because it's a triangle, 1/2 of that, and because delta x, delta y, and delta z are actually 0, then it's 1 rho g times a half times 0. Anything times 0 is 0. So your weight force is actually 0. So we can ignore it and we can just say, well, in the y direction, Py is equal to the P in the S direction is equal to the P in the X direction, and that's Pascal's law. Prove them. So hopefully that makes some sense. Thanks for listening.